Welcome to the math record. Today we'll be covering two sample t-tests and its confidence interval. This video will cover chapter 3, part 2 of our statistics class. Okay, let's get started. A two sample t-test. Okay. The difference between a two sample t-test and a one sample and a paired t-test is that a two sample you get it from two samples. A one sample you get from one sample, and a paired t is basically one sample, but you basically get multiple numbers from it. So like if you're getting like a sample of, let's say, like a bag of marbles, right? Then you get one bag of marbles to get one sample t-test, two bag of marbles to get a two sample t-test. And if you want to compare like like different colored marbles in like one bag, then basically that's a paired t-test, you know? So that's like a general idea how it works, but it's pretty obvious if it's a two sample t-test. Okay? Conditions. This is similar to like basically a t-test, which is it has to be the sample has to be random. So the sample is randomly selected. Sample is random. So it has to be using like a SRS. And then which is a simple random sample. And then it needs to be independent. Independence. So one individual can't affect the probability of another. So just because like you get a red now, it doesn't mean you have to have a red later. So it's not guaranteed. So individual is IND, abbreviated to IND, is independent. Dependent. Okay. And there's a 10% condition. So your sample size, which is n, has to be less than 10% of the population that you're measuring. So because let's say you have 10 as your sample size, that means your population has to be 100 or more. It has to be over 100. And then there's group independence, because if there's ever like two samples or like basically like two proportions or two samples, both of the groups have to be independent of each other. So just because one group got like 30% red doesn't mean like the next group will have like less than 30, equal to 30, or greater than 30. It's gonna be random, okay? It's not guaranteed like that, those amounts. So samples are independent, basically. And then you always had to do the nearly normal condition, like the normal t-test, the one sample t-test, nearly normal condition, which basically states that your histogram is unimodal. So your histogram has to be unimodal, so it only has one peak, and it has to be symmetric. So let's kind of get out of this. I'll draw a picture for you. So basically, like if you have to make a histogram, something, this. Even though it kind of looks like there's two peaks, you could say it's approximately unimodal. The difference between these two like charts is not that much different, or these two. So you basically just say it's approximately unimodal. It's fine if it's approximately. And that has to be symmetric. So this side has to be like somewhat similar to this side, which it kind of is. Um, and like it's the same thing with like basically it's the same method as the t one sample t test. Also, if you have your n, which is equal to like 40 or more, you could just say that its histogram is a unimodal, even though you don't have the data. So if you can't make a histogram, then basically if you have an n that's 40 or more, you could just say it's approximately normal. Or you have 30 or more. It doesn't matter. I usually just use 40 because it's just personal preference. Okay. So the next thing, after you do this, you have to write your transition statement. It's the same case as like a bunch of all the other tests. Just say that your conditions are met. So since the conditions are met, are met, I can construct and then tell what like test can construct. I can construct a 2-sample t-test because that's the one that you're testing on right now. So you're gonna do a transition statement after you check your conditions if they work, and then I'll show an example at the end. Basically, every single one of these tests that I'm gonna show, I'll do an example. A test, our test is gonna be our null hypothesis (HO) is equal to the mean of sample 1, subscript 1, is equal to the mean of subscript 2. And the alternative is either the mean of 1 is less than the mean of 2, or the mean of 1 is greater than the mean of 2, or the mean of 1 is not equal to the mean of 2. Okay, so you're going to choose one of these three. So basically like the same idea of the 2-port z-test, except now you're going to be working with means. Now, after you write your test, basically define your variables. Okay. So, just define your y1, which is your mean of your sample 1. Mean of sample 1. So always put this in context. So just don't write just mean of sample 1. Describe what that sample is. Don't call it sample 1. I'm just using it just as a general idea for you to numerically say. And then you have y2, which is mean of sample 2. It's not obvious with the 2. And then you have SD1, which is the standard deviation of 1. Deviation of sample 1, I'll call S1. And S2 is the standard deviation of sample 2. Deviation of sample 2, basically. And then you have N1, which is just sample size 1 of sample 1. And then you have N2, which is basically the sample size of S2, which I'm just using as a sample, so sample 2. You probably don't have to like define all of these all the time, but it's good for you to know. So you could keep track of what you're using. Now let's actually do the mechanics, which is the math portion. Mechanics, okay. Which is basically now your mean is equal to 0. Your standard error is equal to the square root of your first standard deviation, so standard deviation 1 squared, divided by your basically your first sample size plus okay, make this longer, standard deviation 2 squared divided by the second sample size. So that's your new standard error. There's just a lot of formulas to memorize for like tests basically. And then you have your t-score, which is equal to your mean of sample 1 minus your mean of sample 2 divided by your standard error. Okay. And you're probably going to use your calculator for this because every single time you use a t-test, there's always a degrees of freedom. So I write as D capital of F, degrees of freedom. The formula here is really complicated, so it's not something you maybe want to like memorize because if you're probably just gonna use your calculator to find your degrees of freedom, even which it's gonna be a decimal, it's not actually gonna be a real number, so it's a little strange. I could write it out right now, but basically let me write the rest of everything else. So you have a degrees of freedom and you have alpha level. Alpha level is 0.05. If it doesn't specify it's 0.05, you always just assume it is. If they ask you to change it, then just use the new one. So if they ask for like a 0.1 alpha level, just use 0.1. And then you always make a picture. You always make a picture. So you have your error like this. It's more flattened out than a z-test, basically. And then you basically put the mean, which is 0. and then where you put y1 minus y2, maybe it's like right here or something. So it's y1 minus y2. So mean 1 of sample 1 minus mean of 1 of sample 2, basically. And that's basically it. And then you could just use the p-value to like find the area. So if you have greater than it, then just right here. Less than it would be right here. Alternative is both. You just get one and it's symmetric, so just multiply by 2. So you just get this one, just multiply by 2, or you get this one, you just multiply by 2. Okay, if this is, you don't have to memorize this, but for the degrees of freedom, if you do want to know how to calculate this by hand, it's really annoying and it's really long, and it's basically standard deviation of 1 is squared divided by n1 plus standard deviation of 2 is squared divided by n2. Add those two numbers together, and then you square that number. And then you divide that entire number by 1 all over the first sample size minus 1, and then times whatever that sample size, for the first sample size minus 1, times basically your standard deviation, standard deviation 1 squared divided by your first sample size, and then have that number squared again. Then plus, basically, now this one was standard 2. So you have a sample size 2 minus 1 times the standard deviation 2. Sorry. Sorry, my tablet is not working. Okay. Standard deviation 2 squared divided by n2, your sample size 2, right? And then have that number squared. Sorry, I'm running out of space. But basically, that's how it is. You whatever you get for your standard deviation, square those, and then have those standard deviation divided by its respective sample size, and add those number together, and you square it. And then you do you basically have the reciprocal of is 1 over the sample size minus 1 times basically the standard deviation squared divided by the sample size, square that number and multiply it by those, and then do that for both samples, and then you add them together, and then have that number divide by that number, and that gets you your degrees of freedom. And that's why I say it's really, really messy, because you have squares and another square, and you divide, and you have to subtract numbers. It's just really messy, and it's not something you want to like do by hand, and it's really annoying. But basically, you only need 4 variables, which is your standard deviation of sample 1, your sample size of sample 1, your standard deviation of sample 2, and your sample size of sample 2. So you just need sample 1 and sample 2 standard deviation and their sample size, which is really annoying to do. So what you do is that you kind of just use your calculator for a bunch of these. And then based on what you get for your and then when you use that to find your p-value, you do your conclusion. Okay. Your conclusion is that if your p-value, it's the same case for a bunch of everything. So if your p-value is less than 0.05, you reject the null hypothesis. You reject the null hypothesis and you say the alternative hypothesis is true. And if you have their p-value is greater than 0.05, your alpha level, say you fail to reject the null hypothesis, HO, and you say your alternative hypothesis is false. So basically, if your p-value is less than your alpha level, which is 0.05 usually, you say I reject the null hypothesis, and there is evidence to suggest the alternative hypothesis is true. And if your p-value is greater than 0.05, your alpha level, you say I fail to reject the null hypothesis. There lack evidence to suggest the alternative hypothesis is true. So you're not saying there isn't evidence that says the hypothesis is true. You just say there lack evidence. So there isn't enough evidence to prove that it's true. So you have to write all of this in context. So you have to talk about what your null hypothesis is and your alternative hypothesis is, similar to how you're working with like z-tests and the other t-tests in like a chi-squared, which we're gonna teach in future videos. Okay, Now we're gonna talk, once you're done with the task, sometimes it asks you to follow up with a confidence interval. So let's follow it up with a confidence interval, which is basically confidence interval. Okay. So your mean is going to be equal to your mean of your sample 1 minus your mean of the sample 2, right? And your standard error is basically the same thing, which is just the square root of standard deviation 1 squared divided by n1. This is the square root of the entire thing, okay? Plus standard deviation 2 squared divided by n2, right? So you use your standard error for there, and then you have your mean. Find the thing, you just have the mean plus or minus the t-score, and you have that degrees of freedom that we're not gonna do much on because it's really strange and it's really long. So you kind of use your calculator that times the your standard error, which gets you your your interval for A and B, basically. And then you basically say like I'm something percent confident that the true mean difference. This is the difference now. This is mean a sample 1 minus mean a sample 2. Between the whatever you're looking for in context, always write in context. It's within that interval. Okay, and that's the basic gist. So let's work on an example. Okay, let's delete this. Okay. So we have two tables right here. Throughout the year, student 1, so the first table, the above table, took hundreds of tests, and the table shows there's 40 scores right here. Okay, so the first, we took 40 of his random tests, and we look at all of his scores. And then student 2, a different student, took hundreds of tests, and we took 45 random tests from his hundreds of tests. And the question is student 2 better at tests than student 1? So does the basically is this test oops sorry is this student better than this student? That's the question. So the first thing you do if you ever see a table, you put this in a spreadsheet. So if you have an Inspire, go to your spreadsheet, and then for column A, just label it X. Column B, label it Y. It doesn't matter. Just label them like different. And then column A, which is your X, just put the 40 scores from student 1. And column B, which is Y, just put the 45 scores for student 2. So column 1 is 50, 55, 60, and 365s. A 66, a 67, 370s, a 271, a 72, 473s, a 74, 274s, 475s, a 376s, a 77, a 79, a 80, an 80, an 81, an 83, 485s, a 90, a 95, and a 100. Okay. Now let's put in the data for student 2. So for under column B for Y, put 40, 240s, a 45, a 46, a 50, a 55, a 60, a 60, a 361s, a 64, a 71, another 71, 372s, a 74, a 76, a 78, a 78, a 78, 279s, 380s, 281s, a 82, and 484s, 85, 87, another 87, and another 87, two 88s, an 89, an 89, a 90, 100, and 100. Okay. So go to your and then in your spreadsheet, right? You're gonna go to your third column, which is your column C, and then I mean, never mind. Just go to your press on instead of going to column C. Press on, and then go to your document, right? I mean, not go to your document. Go to the data and statistics, so it's the purple one, right? And then you basically make a histogram for X. So just go to the click to add variables on the bottom one, not the left one, and then plot type, make a histogram. It looks approximately normal, so let me just draw that out. So you have something that looks something along the lines of this, and then you have one right here, a really big one right here, one right here, two right here, and three right here, basically. Right, so you have a histogram like this, so it's like unimodal and it's kind of symmetric. So you say it's approximately normal, and then your second graph, your other histogram. So press the bottom one again, which is your label X, and then change it to Y, so your name of the other one. And you have something like here, this, this. Then you have a gap, and then you have two more. You have one right here, one right here, one right here, one right here. So this graph is a little weird, but you could still say it's approximately normal. You could say this one is somewhat, but not. It's somewhat asymmetric, but it's not really that strong. You could say this is like unimodal, kind of, because there's a peak right here ish. So you could say that it's approximately normal, but you should proceed with caution for this one. For the second histogram, it's a little strange. Okay. So let's now that we're done with that will count as the nearly normal condition. Okay. So let's go on to basically for the other conditions. Okay. So it's random. It's said in our in the question that the sample is randomly selected for student 1 and student 2. So 40 tests from student 1 is selected from over hundreds of tests, and for student 2 is 45 tests over his hundreds of tests. So the sample is randomly selected. So the sample is random. Okay. Usually the question just gives you this, so you can just write this down. And then basically independence. You could just say what logic even if the question doesn't say it, you could basically just say that that the score each student gets in each test is not affected by its previous test, basically. So the test scores are independent, basically. Are independent. Okay. And then you have the 10% condition. So basically the N1, which was 40, is less than 10% of his tests, and N2, which is the sample size of student 2, which is equal to 45, is less than 10% of his tests. Okay? And then you have group independence. So basically, for group independence, you say that the students are independent of each other, are scoring like differently. So students are independent because so just because a student got an 80 on one test doesn't mean student 2 will also have an 80 on his other test, basically. So they won't affect each other, which makes sense. Just because like a student got 100 doesn't mean like another student is guaranteed that 100. Okay. So we already checked the nearly normal condition, which we just said the histogram is unimodal and symmetric for one of them, and the other one you just want to proceed with caution. And then After that, you just write your transition statement, which I'm not going to write now. I'm just going to say it. So since the conditions are met, I can construct a 2-sample t-test. Even though for like one of the nearly normal histograms is not really that normal, we would just say the conditions are like met. We can construct a 2-sample t-test because it should be fine. It's just it's you just want to proceed with caution, but that kind of doesn't really mean anything. You just say that it's just gonna be if the data is a little bit skewed, it's you could just say why it's a little why you can't really use that data, but you could it's still possible to use the test. So you use your test, which is no hypothesis, which your P1. So I mean not your P1, your U1, which is your sample 1 mean is equal to your sample 2 mean, which is the true sample 1 mean. Not from not from the sample. The true mean of sample of student 1's test, and the U2 is the true sample mean of the unit 2's test. And the alternative hypothesis is the question asked, is student 2 better than student 1? So student 2 is better than unit 1, right? Oops, sorry. Okay. So the unit 2 student 2 is greater than 1. So his test average is higher. So based on the alternative hypothesis, it would just be like, is the mean 1 less than mean 2, basically. And then you basically define your variables. So your y1 is your the mean test score for student 1. I'll just call it S1, student 1. And y2 is the mean test score for student 2. And you could write the standard deviation for 1 and 2, but you don't have to. I mean, it's kind of obvious. And then you have N1, which is just sample size for student 1. And N2 is the sample size of student 2. Student 2. Okay. So basically, just write everything in context and define your variables, basically. Okay. Now let's go to your mechanics. So let's just do the math on this. Mechanics. So your mean is 0. It's always going to be 0. Your standard error is the square root of your first standard deviation squared divided by its sample size. So go to your calculator. Go to 1.1, which is your spreadsheet. Go to your spreadsheet where you put in all your data, and then you press go to one of the white rectangles, not the blue one. So go to the white, press menu, press data, press list math, and then press sample standard deviation. Okay, so that's number 7. Press enter, and then press your var button, and then press X. Okay, and then press enter, and you get like a sample deviation, a sample standard deviation of 9.67 approximately. Just round it to like 2 decimal places, fine. So we have 9.67, and that number is squared. And the sample size of the first student was 40 plus. Okay, so now we get to get the sample size of the second student. So go to like a different white square and press menu, press data, press list math, press sample standard deviation, and press var button and press Y. Now the Y one, so that the name of your other column, and then you get a standard deviation of like 14.88 approximately. And then you square that number, and then you divide it by the sample size of that student's, which is 45. Okay. And now we basically need to calculate this. So 9.67 squared divided by 40 plus 14.88 squared divided by 45, and then you square root both that number, and you get a standard error of about 2.69-ish. So rounded, basically. And now we need to do our t-score, which is equal to your mean of your first sample. So go back to your spreadsheet. Okay. So we're gonna use our calculator for this most of the time. And then go to a different white square other than those standard deviations. Press menu, go to data, go to list math again, go to press mean, so number 3, and then press your var button and press X, press enter, and your mean is 74.75 for mean 1, so 74.75. And your mean 2 is, go back to your spreadsheet, menu, data, list math, mean, and go to your Y. And that number is about 74.51. So minus 74.51, right? And then it's y1, so mean of 1 minus mean of 2, and then divide that all by the standard error, which is 2.69. Right? So your answer is 74.75 minus 74.51 divided by 2.69. So you get approximately equal to 0.089 as your t-score. And you're going to have a degrees of freedom or something, but you don't need to calculate that right now. And then you write your alpha level, which is equal to 0.05, right? So now you basically have to find your p-value. So your p-value would be if the t-score, you always write this, the t-score is greater than, well, you set for your null hypothesis, HO, right, where U1 is equal to U2, but mean 1 is equal to mean 2, or alternative hypothesis where you say the question is asking if student 2 is better than student 1, so U1 is less than U2, the mean 1 is less than U2. So we have to say if t is less than 0.089, right? Because if u is less than the u2, then it has become less. If the difference is less than this, basically, then it's gonna become negative, right? So we just have to put this in our whatever the sign is. You always just put that sign. So you basically go to your calculator, go to calculate, go to menu. So go to your calculator, go to menu, go to probability or statistics, doesn't matter. Go to distribution, and go to your TCDF, the number 5, right? And then you have negative E999 is actually go to menu, go to statistics number 6, and go to your stats test, and then go to your 2 sample t-test, which is number 4, and then press stats. You change your data to stats, and then go to OK. So the mean of 1 is 74.75. The standard deviation of 1 is 9.67. Remember, it's right here. And our sample size of 1 is 40. Our mean of 2 is sample 2 is 74.51. And our standard deviation of 2 is 14.88, right? Right here. So you just plug in all the variables. And 2 is our sample size of 2, which is 45. And then the question is, if it's, go to your, and then you write the alternative hypothesis, change it to U1 is less than U2. So, because that's what our alternative hypothesis is, right here. If student 2 is better than student 1. Always put it as no, and put OK. Right? And then that number basically gives you this test gives you everything. So it gives you your t-score, which is 0.089, which you got right here, which you did the math on. Our p-value, you just write this out, which is less than the t-score there, is equal to 0.054-ish, rounded to 2 decimal places. It's like 0.535375, etc., but just round to like 2 decimals. Your degrees of freedom, right? Your degrees of freedom, and that's why you can't use the TCDF, because you don't know what your degrees of freedom is. So your degrees of freedom is equal to 76.31. So just I usually write as 2 decimals for just degrees of freedom for 2 samples, because it's really strange. And then you have mean 1, which is 74.75, mean 2, which is 74.51, right? It's shown right here. Standard deviation 1 is 9.67, right? And then standard deviation 2 is 14.88. And then sample size of 1 is 40, and sample size of the sample size of student 2 is 45, right? So you have a p-value of 0.54, which is obviously way bigger than 0.05, right? So that's your alpha level. So you write down your conclusion now, basically. Actually, sorry. You make a picture. I forgot the picture. So let's just make a mini picture right here. I'm running out of space, but split this. Your mean is 0, because the mean is 0. Your standard error is 2.69 right here, so 2.69. And your difference between those two numbers is 74.75. So kind of do the math on this a little bit. So 74.75 minus 74.51 is 0.24. So it's somewhere right here, 0.24, right? Which is y1 minus y2. And then your thing is asking is if once it's if u1 is less than u2, so anything less than this number, so it's all this area, right? So it's just general idea. If it's less than it, just put anything to the left, basically. So this area, which we calculate from the p-value, is 0.54. I'm sorry if it looks like a little bit off, because I'm not the best at drawing, but basically that's the probability, 0.54. So draw your picture, okay? X this out. And then you do your conclusion. Okay. So based on on the p-value of 0.5 0.54, right? 0.54. I fail. Wait, sorry. Of 0.54, which is, because you got compared to the alpha level, which is greater than the alpha level of 0.05. I fail to reject the null hypothesis, so the HO. And you say they lack evidence. Lack evidence. Sorry. Evidence to suggest the alternative hypothesis, which HA is true. True. So you have to put this in context. So basically, you're right. Based on the p-value of 0.54, which is greater than the alpha level of 0.05, I failed to reject the no hypothesis that student 1 is the same level in his test score than student 2. Their lack evidence suggests that the alternative hypothesis that student 2 is better than student 1 is true. So you're basically saying in these two sentences that there isn't enough evidence that say that student 2 is better than student 1, and that you think that student 2 and student 1 is about the same level in their test scores. Okay? So that completes your hypothesis test. And if they ever ask to follow up with the confidence interval, right? Confidence interval. So basically, now you have your mean. Your mean is y1 minus y2. So remember the number was 74.75 minus 74.51, which is equal to, so we have the mean 1, which is 74.75, minus the mean 2, which is 74.51, which is equal to 0.24. And then we have a standard error, which is equal to basically what we had. So remember, our first standard error was like 9.67. I mean, standard deviation for sample 1. And then our mean was, our sample size for 1 is 40. Plus our standard deviation of 2, which is 14.88 squared, or this entire thing, divided by its second sample size, which is 45. So that number was 9.67 squared divided by 40 plus 14.88 squared divided by 45, which was 2.69. Roughly 2.69. Right? So we have that. And then we could put the mean is plus or minus the t-score. Oops, sorry. T-score of what your area want it to be times the standard error. Since for 2 samples, every single time you do the t-score, you get a really weird degrees of freedom. We're basically just gonna always use your calculator for this. So we basically just write out the work if you want, basically. But then you had to use your calculator all the time when you had to like do 2 sample t-tests because of the degrees of freedom. So you go to your calculator, go to statistics, which is number 6. Go to your confidence interval, which is number 6. Go to your 2 sample t interval, which is number 4. Press enter. Change your data to stats. So data input method is equal to stats. Okay. And then x1, just type all your variables in again. So mean 1 was 74.75. Standard deviation 1 was 9.67. Your sample size of 1 is 40. Mean of sample 2 was 74.51. Standard deviation of sample 2 is 14.88. Sample size of sample 2 is 45. And you want a 95% confidence interval. And pool, no. You never pool. So press OK. And basically get all the statistics. So your interval is negative. So you're doing a 95% confidence interval. You have negative 5.125. Actually, let's say 5.13. We will just round it up to 2 decimal places. Comma. And then the upper one, C upper, which is the upper confidence interval, is 5.61. Right? And then you have your mean error, which is 5.369, which is basically just your t-score times your standard error. So if you ever want to find your t-score, you basically just do this. So you have your mean error, which is like 5.37 rounded. So you have 5.37. Divide by your standard error, which is 2.69. So divide by 2.69. So a t-score of 95% area with a degree of freedom of 76.31, which you get from the confidence interval when you plug it in, is about 2. And then you basically say that when you write this word down is basically you write in words, I'm 95% confident that the true mean difference between you write this in context. I'm 95% confident that the true mean difference between student one's test score and student two's test score is within the interval negative 5.13 to 5.61, basically. So you can also use, as always, you can always use the confidence interval to help you answer if the answer of the hypothesis test, kind of. Because basically, if you have if the difference is so the difference is alternative hypothesis 0, right? So the 0 is between negative 5.13 and 5.61. So since 0 is between it, that means there is a chance that the two students are equal to each other. And so there is a chance, that means the student 1 and student 2 might have the same testing average for their scores. So you can't say student 2 is better than student 1. So you can also use the confidence interval for that. So basically that covers the two sample t-tests and its confidence interval. Thanks for watching, and I'll see you at the next math record.